Okay. Well, I guess, what do you guys want to do? Do you want to hear about invertible matrices, or do you want to, we're going to find the inverse of a matrix using Gauss's method. So do you want to do this or work on, like, spend a little bit of time working on your homework? Maybe I've tired you out. So Catherine and Ramiz, what do you guys want to do? Catherine says, let's see. Okay, well, Catherine, let's see, Ramiz answers 1524. What does that mean?
I think if you scroll down.
Oh, it's different. Not sure. Okay, 1524 was an answer to the previous question. Good, that's a good thinking. I think, do you want to do homework or a thing? 1524, some code. Okay, so why don't I briefly tell you how to do a matrix inverse, and then we'll go and do homework. So this will be really quick. I'll just give you the basic idea. If I want to find, let's say I wanted to find whether this matrix here has an inverse or not. What I do is I form what's called the giant augmented matrix. It's augmented because I put a bar in it. Then over here, I put the identity matrix. Then I'm going to do row operations with this whole matrix where I treat each row as 1, 2, 1, 0, and 3, 4, 0, 1. So I could do here -3 times row 1 plus row 2. Would give me 0 there, right? Because 3 times 1 is 0, and then 2 times 3 is -6, plus 4 is -2. And then -3 times 1 is -3, and 0 times, right? So that's like a minus is cancels that. 6 -6 plus 4 is -2, and -3 is -3. Okay, so I need to do reduced row echelon form. The goal is to make this into the identity matrix. So I can do row 2 plus row 1. Because since this is leading, we need to get rid of that one there. 0, -2, -3, 1. And we're going to do 0 plus 1 is 1. -2 plus 2 is 0. -3 plus 1 is -2. And 1 plus 0 is 1. Then the last one is I divide row 2 by 1, multiply it by -1/2. To change this into a 1, because that will put this matrix into reduced row echelon form, and it won't change this, but it will change this one. That will be 3/2, and this will be -1/2. Now, if I haven't made a mistake. So what I've done is I started with the identity matrix over here and did row operations until I got the identity matrix over here. Because if it's invertible, you're going to end up with the identity matrix, and it's going to turn out that then this matrix, the other side's the inverse. So what I can do is check that. Here's 1, 2, 3, 4, and I want to check, is this the matrix? Well, if I haven't made a mistake, then this should end up being the identity matrix. Or if I've made a mistake, that should reveal that. Well, this is -1 times -2 plus 2 times 3/2. Well, 2 times 3/2 is 3, and 3 plus -2 is 1. That's good. How about this one? This is 1 times 1 plus 2 times -1/2. 2 times -1/2 is -1. 1 plus -1 is 0. And this one is -2 times 3 is -6, plus 4 times 2. Well, 4 times 3/2. Well, 4 times 3/2, the 2 cancels one of the 2's and the 4. 2 times 3 is 6. You get 6 plus -6 is 0. And then you have 3 times 4 times minus a half. 4 times minus a half is minus 2. Minus 2 plus 3 is 1. So indeed, if this is the matrix A, this is the inverse, and we found it with Gauss's method.
When you originally sent to set it up with identity matrix, what is that whole giant matrix?
This is called the giant augmented matrix. So it is the most computationally efficient way to find inverses of numerical matrices. So if you want, there's sometimes you may know a formula for an inverse, or other things, but this is the most efficient way to find inverse matrices.
So in theory, if you had a system of equations and you wanted to find the inverse of those system of equations.
Well, there's an inverse of a matrix.
So you take the system of equations, you change them to a augmented matrix, and then you wanted to find out the inverse of that. So say that you found out the inverse and then you turned it into a system of equations.
I think what you're
then would those lines be like parallel, like if they were inverse, or
okay, so first of all, inverse only works for square matrices, right?
okay.
So if you had a linear system involved, you'd have something like this.
Yeah.
Well, this is, say, a 2 by 2, this is a 2 by 1, and a 2 by 1. Now, what you do is you take this and look for its inverse.
Yeah.
Now, if you found it, what would you know? Well, you'd know that A inverse A equals the identity matrix, right?
Yeah.
That's the point. Well, that means that A inverse A times X equals A inverse times B, because this is just a name for the same matrix. So all I've done is taken this one and replaced it with this. So then this is true if I can find an inverse, but the A inverse A is the identity. So this becomes X times the identity equals A inverse B. And the identity times X is X. You have X equals A inverse B. So if this matrix here, it can be any linear system that's n by n. If there's an inverse, it's going to have one solution, and this is the solution. You can find by multiplying the constants times A inverse to find the thing. So it automates finding. It's an alternate way. We use Gauss's method to find the inverse, and then you can just use that inverse matrix to find solutions. The advantage of this is if you know A inverse, you can just plug in different B's and you get the solution out.
So only square matrices
have inverses.
Can have inverse. Okay.
So this only works for a subset of linear systems where the number of equations equals the number of variables. So if you have more equations than variables, or more variables than equations, you don't have an inverse. You have to have exactly the same number. Okay. So